Hello. In this work entitled Implementation of Artificial Neural Network for the Optimization of a Wind Farm, I will present an optimization approach for wind farm using artificial neural network model. The evolution of the establishment of a wind farm in recent years pushed the designer of wind farm to provide more effort in the optimization in order to reduce the effect of wake and to maximize power. Our objective in this present work is to test the optimization of wind farm using artificial neural network. In the first study phase, we will try to choose the wake model, artificial neural network wake, which allows to standardize the losses of wake and to maximize the power. The second study, a genetic algorithm is applied based on the information collected from artificial neural network wake power model, and they are exploited in the second optimization. This allows to find the yaw angles optimal according to the wind direction in the studied wind farm. I will start with a presentation of the wake model used in the study called Johnson model. As shown in figure 1, the speed deficit in the wake of the wind can be expressed as follow. Equation number 1. And we can notice that the input speed is a function of incoming wind speed, thrust coefficient, rotor radius, and the wake radius. Artificial neural network wake model. The objective of our model is to predict the energy produced from a wind farm, taking into account the conditions of the wind farm, such as the direction and the speed of the wind and the yaw angles. As shown in figure number 2, the process begins with collecting data on wind turbine, wind speed and the direction, and the yaw angles. After verifying the standardization of wake losses, the artificial neural network wake model is established. Unlike traditional models, the design of our model targets the overall wind farm rather than the individual wind power treatment. To validate our model, the artificial neural network wake model will be used in a sharing wind farm to assess its power. The location data of the wind farm are summarized in table number 1. The wind turbine used in the sharing wind farm is of the UP77-1500 type. The table to summarize these characteristics. Methodology. The power sought by artificial neural network way is included in the output layer. The speed, wind direction, and the yaw angle are all included in input layer. We will have 17 neurons in this layer. There are also two hidden layers containing 22 neurons and 16 for neurons respectively. 64 neurons respectively. Figure 3 clearly shows in the form of diagrams the structure of artificial neural network wake. The equation used in the layers of our model are noted below. Equation number 2 and equation number 3. Sigmoid function and the rectified linear unit activation function. To have visibility of the performance of artificial neural network wake model, we calculate the coefficient R squared noted in equation number 4. And according to the value in table number 4, the artificial neural network wake model is very efficient since it takes into account the wake effect, and also all the value of R square is tends towards the value 1. Figure number 4 shows the optimization process using the genetic algorithm. The objective function is to be optimized in is the total power ratio. In this part of the study, we will use the genetic algorithm to evaluate the power ratio noted in equation number 5. The ratio power equal actual power generation by theoretical power generation. Results and the discussion. In figure number 5 shows a comparison between real data and optimized power ratio data. The speed used in this study is assumed to be 9 meters per second. The optimization results show that the energy maximization is obtained in the direction comprised between 164 into 180 degrees. It is recalled that this optimization is carried out between a direction range 115 degrees and 200 degrees, and the yaw rotation angles comprised between plus 20 degrees and minus 20 degrees. The increase in the power ratio, which tends toward the value 1, is explained by the fact that the angle of the turbine are optimized so as to have minimal and uniform wake losses. Figure C and the figure 7, the wind turbine 1, 2, and the turbine 5 are grouped in the direction range between 117 degrees, 70 degrees, and the minus and the 118 degrees. These results seem logical and agree with the first study. We also justify the optimization of the angles in this direction by the minimization of the wake effect. On the other hand, the wind turbine number 3 and number 4 have several direction and different yaw angle values. This can be explained by the position of these wind turbines in relation to the upstream and the downstream wind turbine in order to minimize the wake. Conclusion: in this present work, we try to develop a new model based on neural networks to predict the energy of a wind farm. The optimization results applied to a wind farm containing 5 wind turbines showed the efficiency of this model, which was able to improve the studied power ratio up to 0.97 in all directions. Subsequently, another optimization process based on the yaw angles of the turbines. This process uses a genetic algorithm to improve the power produced by a wind farm and standardize the wake losses. The study shows the importance of installing the neurons network in wind farm optimization studies. Note also that this type of study requires a large amount of data to have very precise results. In the next studies, we will try to test this model on highly terrain with a large number of wind turbines. Thank you for your attention.